Hello and welcome to KETIV Virtual Academy. My name is Tyler Hart. I'm with the marketing team involved in running these weekly training and thought leadership sessions. And today's topic is parametric design studies made easy using Ansys simulation. Your expert for the day is Snigdha Sarkar, a simulation practice leader here at KETIV. If you have questions for Snigdha during the session, please submit them to the Q&A, different than the chat. At the bottom of your screen, much easier to answer those questions in the Q&A, and we will either address them during the session or afterwards. Also, these are all recorded and available for distribution on KETIV.com or our YouTube channel. I'd also like to quickly mention an event we have, a series of events we have coming up called the Manufacturing Innovation Workshop. We actually had one last night in California, and it went wonderfully. We had a bunch of business leaders and technical leaders together talking about challenges, talking about solutions. It was a great time had by all. And we'll have these around the country through December. So definitely scan this QR code or go to our homepage, find the sign up button and claim your spot. There's limited spots for these events. Definitely a great opportunity to network and have a happy hour with everybody. So without further ado, I will pass things over to Snigdha to kick us off. Snigdha, thank you so much for being here.
Thank you so much, Tyler. Can you hear me okay?
Absolutely, yes.
Excellent. All right. Hi, everyone. My name is Snigdha Sarkar, as Tyler mentioned. Welcome to today's Virtual Academy session. Today, we're going to be talking about parametric modeling and parametric design studies using Ansys simulation tools. This is a first session in a series of 4 sessions where we explore designs using different simulation technologies and tool sets. And we're going to be focusing on Ansys Discovery today. We've done a couple of KVAs in the past on Ansys Discovery, but the one today is going to specifically focus on how to set up parameters and why it's important for us to engage in early design exploration. Speaking of which, let's talk about the agenda. I'll go over the motivation of why we need to explore designs early on in the product development workflow. And then we'll go over to Ansys Discovery, look at a fluid thermal simulation example, and then I'll show you how to set up parameters and what type of simulation data we can gather from these runs. Like Tyler mentioned, if you have questions, feel free to leave that in the chat box below, and we'll get to it towards the end of the simulation. All right. So speaking of the need for early design exploration, I think one of the top challenges in manufacturing industry today is somehow being able to reduce your time to market, right? You want to make your product development as efficient as possible. But what generally ends up happening is you have a team of design engineers who are going through multiple design iterations. And once they have some sort of confidence in their design, they send it forward to the analysis team or the simulation team, wherein simulation experts will add more fidelity to your simulation. They'll look at more accuracy for results, and they'll give you, a comprehensive picture of what you can expect. But the problem is, if that design needs to be revised, if there are changes that are needed in the design, then this entire process is repeated. So you have to do multiple back and forth between the design team and the analysis team. And this ends up being a huge time drain on the product development process. So the question is, how can we help the simulation experts, speed up their process, offload some of the work? Because we all know that in terms of simulation skill set, companies have limited resources. So that can end up, in a lengthy turnaround time, correct? The other challenge, with not using simulation early on is, most of the costs in the design process, they are locked in the early stages, but simulation is hardly used in these stages. So what happens is during conceptualization or ideation, you're working off based on legacy designs or empirical data or hand calculations. Whereas if you were able to leverage simulation early on in the design workflow, then you'd be able to make much better decisions about how to proceed with the iterations or the changes that you make to your geometry. The problem is if you try to make the change after the product is already designed, already developed, it becomes really costly to, incorporate that change into your problem, right? So right now, conventionally speaking, simulation is used, right before prototyping or somewhere around testing, but we want to make sure that simulation is used early on. And for that, we need to enable even design engineers to be able to use simulation tool sets, right? So how do we do that? Well, Ansys Discovery is the perfect solution, not just for the design engineers, but also for the simulation experts. What happens is a tool like Ansys Discovery can really help democratize, simulation technology for everybody involved in the product development workflow, right? For simulation experts, they are now able to offload some of the routine preliminary simulations that people might need to do in order to come up with the best design decisions. And that leads to, faster turnaround time, that leads to robust geometry prep, and ultimately, that opens up, the bandwidth and the resources in terms of simulation expertise for doing more high level, high fidelity simulations. For design engineers, now that they're able to use simulation technology to guide their design decisions early on, they're able to reduce that back and forth between the design team and the simulation team. So the good thing about Discovery is you don't need to be an expert, even if you're just, a design engineer and you haven't had much experience with simulation. The tool is easy and intuitive enough for you to pick it up and run with it and make changes to your design and see the effect of those changes in real time. Okay, so that's what we're hoping to demonstrate using the example that I'll show you in just a second. Okay. So the idea is to make your product development workflow as efficient as possible. If Ansys Discovery is the right tool set for you, or if you relate to this type of a workflow wherein there's a lot of back and forth between the design and the analysis teams, then hopefully this KVA is going to be useful for you. So with that, let's switch over to Ansys Discovery and look at the problem that we are going to try and simulate and parameterize today. So hopefully you guys can see Ansys Discovery open on my screen. I'm working with the latest version, which is 2023 R2. Like I said early in the KVA, Ansys Discovery is a tool set that's being rapidly developed. With every release version, there are more and more capabilities that are being added. Let me actually go to the model stage and talk about the geometry that we're going to be evaluating today, and then we'll move on to the simulation part. Now, some of you who are already familiar with Ansys Discovery know that Discovery is a multi-purpose tool. Sure, you can do simulations with it, but it's a very powerful CAD prep tool as well. So no matter which native CAD toolset you're using today, when you have to get your geometry ready for simulation, whether you're doing that simulation inside Discovery or you're going to export it to some other flagship solver, Discovery is a great tool for that. You can use it as a direct modeler to easily make modifications to your geometry. And I'm in the model stage. This is where you would be making those modifications. And this is very similar to another Ansys CAD prep tool called SpaceClaim. Maybe you guys are more familiar with that. This is very similar to it. A lot of the functionalities and tool sets have been carried over into Discovery so that the learning curve is not that high. And you should be able to pick it up quite intuitively. Now, speaking of the geometry that we have on the screen, it's a very simple enclosure for an electronic device. Let's go over the model tree one by one. So what we have are these heat loads right? So these are usually, some sort of energy storage heat loads, let's say, for example, and we will be assigning, a unique wattage to each and every one of these heat loads over here, right? And you also have two fans that are blowing air inside this enclosure. Now, when I got the original geometry, I had the fan available from the vendor, etc. So I just went ahead and, simplified it and, made these fan zones. But Discovery gives you the option of, adding fan intake boundary conditions, so you don't even need the casing, etc. So it can be even simpler than what I'm showing you on the screen over here. This is the enclosure, the cabinet inside which these heat loads are placed. At the back of it, you see some grills. These will act as, the outlet boundary condition for this particular problem. And then you have a board at the bottom over here, just, as an additional conducting path. Realistically speaking, there are many more components that can be added to a problem like this. You can have bus bars, you can have control units. Every component can be a heat sink or a heat source, right? But in this case, let's keep it simple, and we'll try to set this up and see what happens, okay? So this is in the model stage. If you wanted to make any changes to the geometry, like I said, you can do it here. You can go ahead and use the pull functionality to extrude a particular face. You can go ahead and move different things. Fairly easy to do all that, okay? So let's see how we have set this up for simulation, okay? So in order to access simulation, we switch from the model stage to the explore stage over here. The model stage is for the geometry prep part. It's common no matter which workflow you use, whether you do your simulation and discovery or some other tool set. The explore stage is for discovery only simulations, right? Okay. So because this is a fluid thermal simulation, materials play a very important role. You'll see in the physics tree that we have a number of different material assignments. Again, these are not accurate by any means. This is just an example problem. So, I've assigned some example materials to this particular simulation setup, okay? If you go over, these individual volumes, the components that show up in the model tree, Discovery will tell you which products or, which materials I've selected. So say, for example, the board is some thermoplastic. If you look at the enclosure, it's set as air. Same goes for the fan zone over here. This is air as well. And then, you have these heat loads that have been, again, assigned some other solid material, right? So you can always go ahead and change the properties inside these materials that you choose from the Discovery database. If you have other products like Ansys Granta, then your database increases even further. You can create a new material and store it in the local library as well for reuse in your next simulation. So a lot of functionality with how you are using and assigning materials to your discovery simulations. Okay. Now, once we have the correct material assignment for each of the volumes in my simulation, it's time to think about boundary conditions for this particular problem. So like I said, we have two intake fans over here. We have, the grill open to ambient conditions. We have these walls that can either be adiabatic, or you could apply a convection boundary condition depending on, how you're setting up your problem. If this were sitting in, ambient conditions, maybe you go ahead and assign a nominal heat transfer coefficient to it. If not, you can also just keep this as insulated wall, right? So what we have done is we've assigned, certain heat loads for these cubes that you see over here. So if you look at the physics tree, let me go ahead and collapse this. Yeah, if you look at the physics tree, all these heat loads have been assigned to these cubes over here. You can also club this into a single condition. But if you wanted to have individual values for different heap sources, then it's wise to sort of segregate them. And the moment you add a heat load, right, Discovery automatically knows that it's going to be a thermal simulation. The good thing about Discovery is it's not just limited to any one physics. As you can see on the panel over here, you can do structural simulations, fluid simulations, thermal simulations, and also electromagnetic simulations. You'll just have to check whether the capability that you want to model is included within Discovery or not. Right. So the moment you add heat loads, Discovery knows that this is going to be a thermal simulation. So what it does is it automatically assigns a convection boundary condition on those walls that have no other condition applied to them. So say, for example, these walls, these pink walls that are adjacent to the fan casing, they have already been assigned a convection boundary condition. The default value is around 10 watt per meter square Kelvin. I changed that to 5 just in order to be a little bit more realistic. And if you look at the other walls in the domain, the walls that form the enclosure, these have been assigned as slip walls, right? Similar to any other CFD simulation that you set up. If you double click on them, you'll notice that these are insulated. But if you wanted to add another thermal boundary condition to it, Discovery has a lot of functionality now. Even radiation is available, as you can see on the screen. So you could go ahead and assign any other thermal boundary condition. For this problem, I'm just going to leave it at insulated. But like I said, if you wanted to apply convection boundary condition to the enclosure walls, that is a possibility as well. Okay. All right. So now that we have talked about these thermal boundary conditions, let's talk about the fan intake and the outlet. So the fan intake boundary condition has been applied to this guy and then this other face, right? So if I double click on this, you will notice that the heads up display, the HUD as we call it, shows up. So it gives you a little bit more context into the boundary conditions that have been applied. Now, the good thing about Discovery is that it automatically has a lot of fans and fan curve data loaded into it. And this is from the Ansys IcePack library. But if you wanted to, input a custom fan curve wherein you have a dP versus velocity curve, or a dP versus volumetric flow rate curve, you can do that as well. So for example, in this case, I created a dummy fan and I added it to my local library, right? So you create it once and it's available to you for future simulations. That is why you see this option of remove from local library showing up. But if you click on this drop-down menu, you will notice that there are other fans as well. And these are fans that are commercially used. So if any of it matches the fans that you have in your problem, then you can directly go ahead and use those. Okay. So both this surface and this surface have been denoted as intake fans. That is why you have these two boundary conditions. And then this guy over here, the fan outlet, is the outlet boundary condition. This is where we have applied zero gauge pressure, right? Now, I've also assigned an inlet temperature for the fan flow at around 20 degrees Celsius. Again, this was not the default value. You can go ahead and change it depending on your conditions. Okay. So apart from, assigning all these conditions, Discovery is pretty smart, pretty intuitive. What it automatically does and, saves us some manual labor is it automatically determines bonded contacts. So if you were to prep your geometry for simulation in any other software, you'd have to ensure that the interfaces are connected and they're shared so that you can generate a conformal mesh. But Discovery is very smart, so it does that automatically. You don't have to go through that shared topology step. If you're doing the simulation inside Discovery, it'll automatically detect contact pairs, and that's what you see on the screen. It'll also detect all the fluid solid interfaces. So wherever, a solid wall is in contact with the surrounding air, those are the surfaces that you see highlighted on the screen right now. Okay. All right. So now that we've gone over the simulation setup, Again, if anybody has any questions, feel free to leave that in the chat box. I'll definitely get to it later on. We can go ahead and run this simulation. This is the simulation information display box, right? We call it SID. This is the area where you'll be able to see the simulation progress. So let me go ahead and run this simulation. This is the results arc. I just go ahead and click on the solve button, and it's going to start solving the problem for me. And so you can immediately start seeing the temperature results as the solution is progressing. Like I said, if you look at the SID, you'll see a white tracker that's going all along the periphery of the hexagon, and that tells you that your results are still converging. Once that white tracker goes away or these values become static, that's when you know that you have a converged solution. Okay, so we'll just give it a second. And by the way, the reason why you can see instantaneous results is it is using GPU compute technology in the background instead of CPU technology. And so as you keep making design modifications, the results change in real time. So you can see if you've made the right decision or not. Now you can see that the white tracker has gone away and the numbers are no longer changing. So we already have a convert solution over here. And what you see on the screen in terms of a result are the contour values for temperature. You could change this to velocity and, it would show you the velocity contour instead. Similarly, if you were looking to do a simulation wherein, turbulence was important, you could go ahead and, look at vortices as well. Right now, it's only showing you, the wall conditions. And then you could also look at pressure. You could also look at heat flux, right? And you can see that the heat flux is only available for the heat loads, right? Because that is where your heat is coming from. This is all 0, all right? So let's go back to temperature because that's our major concern in this case. If you want, you can also look at other post-processing variables, like say, for example, here you can see a cut plane with the temperature path lines. Let me change this to velocity and that will make a little bit more sense. So really pretty pictures. And what I also have in this simulation are monitors to look at values at any particular location. So say, for example, if you wanted to look at the velocity of the fan at any one particular inlet, you could go ahead and look at it. This might be a good way to gauge if your fan is operating, in the optimal range, because you can look at the velocity and then estimate the pressure drop based on the curve that you've specified. Like I said, I'm using a dummy fan, so my values are a little arbitrary. But for your case, when you have a real dP versus velocity curve, you'd be able to tell, which range your fan is actually operating in. So this is just the average velocity of the fan at this location. Similarly, I have one for the other fan as well. And then, I have one for the maximum temperature at any one particular heat load. So any surfaces or any components that you have in your domain, you could set up a monitor for it and look at values specific to that particular zone. Okay. Now, the advantage of having these monitors is not only to get a value at the end of your simulation, but also be able to track the changes in these values as you keep making more design modifications. So say, for example, let's go back to this guy. And let's go to temperature, okay? So say, for example, you have this design over here, and you are going to make some changes to this design, right? So say, for example, let's just do this, right? Let's go ahead and pull this guy a little bit. And now your design has changed, and Discovery automatically knows that a design variation has occurred. So what it's going to do is it's going to start recalculating the results, which is why you see that the solution is being regenerated. And again, you can see this white tracker going around the SID. So because you've made a modification, it's going to update the real-time simulation results that you see on the screen. And so in a second, we'll have another design point, and we can compare it to the results from our original case. So that is, what we are going to see in just a second. And the monitors will show you if the values have declined or have they improved. And you can then determine whether your design decision was correct or not. So say, for example, if we're looking at the heat load maximum temperature for this first body over here, you will see that by making the enclosure a little bit longer, your heat load maximum temperature has increased. So if that's contrary to what you want, then you know that this is not the right direction to proceed in. Okay, so this is how you make a manual change in your geometry and evaluate results real time. But we're talking about parametric modeling, right? How do you set up parameters? And that's what I'm going to be focusing on. So let me go back to the model stage. Okay, because this is where we're going to set up a geometry parameter and then see how it can be varied as per simulation goes. Okay, so let me only keep the things I need. I'll just go ahead and keep the heat loads and the enclosure over here. Okay. All right. So let me just box select this guy and hide other faces. Okay, excellent. All right. So say, for example, I'm designing this enclosure and I don't know how to space my grills or where to position them. Should they be a little bit higher up? Should they be lower in my box? I'm not exactly sure, right? I don't know what is the optimal location of the grills. And maybe it doesn't make that much of a difference, but I have to verify it somehow, right? So that's where parametric modeling comes into the picture. So let's say we want to move the position of the grill with respect to either the heat loads or with respect to the overall enclosure. Like, how do we go about doing that? Okay, so what we're going to do is we're going to go ahead and select any one particular grill. Okay, I can also go ahead and box select everything. That would be convenient. But to just show you additional trick, you could also use something called power select, which is a very handy tool to simultaneously select multiple features in your geometry that have the same characteristics. Meaning, if I want to select multiple surfaces that have the same area, I could use this power select feature, and it's going to detect everything in the visible geometry automatically. Okay, so let me go ahead and collapse this. Now I want to move this, right? So I go ahead and select the move functionality. All right. Now, a couple of steps here to make sure that I'm setting up the parameters correctly. Remember, a geometric parameter always needs to have a reference, right? The solver needs to know how to vary the distance and where to vary the distance from, right? If there's no constraint, if there's no reference, then it's difficult for the solver to know exactly which direction or which reference point to measure the distance from, right? So that's what we are going to do. Okay, so first of all, I'm going to go ahead and anchor my move tool to a different location. I find it to be more convenient if the anchor is not right in the middle of the selection, because then it's difficult to estimate the distance by which I need to move my components. So I'm just going to go ahead and choose this guy over here as the new location for my move tool anchor. Okay, so this way I know exactly how much distance I need to move these grills by. Okay, the next thing that I want to do is check maintain orientation. Whichever surfaces and instances I have selected, I'd like them to maintain their orientation as they're moved from location A to location B, right? The other thing that I'm going to do is choose the direction in which I want to move my bodies. Well, in this case, surfaces, right? Because again, the direction is important. Otherwise, the distance can apply to any of the directions. The moment you select this axis in the move tool, right? This vertical axis in the move tool, you will notice that the add a geometric parameter option has been activated. Okay, it wasn't active earlier because the solver did not have enough information about how to vary that distance, right? It did not have the guardrails or the reference points to measure that distance from. But the moment you select the axis, this becomes available. Now, I want this distance to vary with respect to, say, for example, the bottom of the enclosure. So what I'm going to do is I'm going to go ahead and choose ruler. And what that does is it fixes one end of the ruler on the location of the move tool, right? So I just anchored it to a new location. So that's one endpoint. And then I want it to be varied from the bottom of the enclosure. Okay, so this is the distance that I'm going to be working with. This is the distance I'm going to be varying in several parametric design studies. Okay, so I go ahead and make this a parameter. So this is the option for adding this ruler dimension as a parameter. So I'm just going to go ahead and click on this guy. Okay, let's hit escape to get rid of the HUD. The moment you create this parameter, you will notice this little guy showing up right next to the SID. You click on this and you'll see the parameter that you've just created. Okay, so this is the distance between this location and this bottom location of the enclosure. Okay. Now, one best practice that I can recommend is if you're going through a few variations and not a lot, you might want to check the different values of the parameter you've set up before you go to simulate it, because sometimes what happens is, there might be intersections or, the geometry may not be able to modify correctly based on the distance you've specified or the angle you've specified, anything that you're parameterizing, right? So let's quickly go ahead and check if changing this value successfully changes the location of the objects that I wanted to move, right? So let me go ahead and make this 132 millimeters and see if it is successful. Okay, so it works. All I did was I changed it to 132 millimeters and hit enter. Let me also go ahead and try 130 millimeters and see if it works. Okay, so it works again. Okay, so now I have three design points. I have 135, I have 132, I have 130. All right, so maybe we can set up the variations accordingly. So once I have this geometric parameter created, let me go to the explore stage, because this is where the simulation is going to take place. And again, the parameter is carried over here. Along with the geometric parameter, let's also go ahead and assign one of the boundary conditions or cell zone conditions as a parameter, right? Because you may not just be evaluating different design scenarios. Maybe you're also looking at different what if scenarios, right? What if my heat load was higher? What if my temperature was lower, right? Things like this that you may need to vary and explore the entire range of possibilities. So what we'll do is we'll go ahead and make any one of these heat loads to be a parameter. Okay, so this is the symbol for the parameter. You must have seen it when I created the geometry parameter. Again, it shows up next to all the fields that can be parameterized, right? So we went ahead and added this as an additional parameter. Okay, so let's go ahead and look at this table over here in the explore stage. Notice the two columns that you see over here. One is for the geometry parameter that you just set up, and one is for the heat load that you just parameterize. So both of these can be varied simultaneously or sequentially, depending on what you want, correct? So let's go ahead and add a few variations, right? So let's make this 135. Let's make this 132. And then let's add another one, which is 130. Okay. And maybe we'll also go ahead and change this guy to 20 watts. Okay. Now, The other thing that you will notice about this table is that all the monitors that you set up originally, right, for your base simulation, they also get populated. So you'll be getting the values for each of these design variations. And that ways you can see whether your actionable results or, the deliverables that you're looking for in the simulation are getting changed for the better or worse, right? So all I'm going to go ahead and do is update all, and then it'll automatically run in the background and give you multiple simulation cases and results for the different variations that you've set up. Okay, so this is going to take 1 or 2 minutes to complete. In the meanwhile, let me check if we have any questions. I don't see any questions so far. Now, all the steps that I'm showing you today, they can also be automated. There's a functionality in Ansys Discovery with which whatever modifications you're making to your geometry, those can all be repeated through something called history tracking. And that is another cool feature to, make your workflow even more efficient, because it takes out a lot of the manual work that you're doing to set up these parameters, right? So if you guys are interested in learning more about how to automate some of the repeatable design or CAD cleanup work that you're doing for setting up your simulations, feel free to reach out to us, and we'd be happy to provide you with more demos and resources. You can always reach out to us at support@ketiv.com, and we'd be happy to get back to you. So you can see that the simulations are taking place in the background, and every time a variation is computed, you'll see this green symbol right next to it, which basically means that this solution is now available. And you can almost consider the monitors that we set up as output parameters, because just like you would find in a design point table from Workbench, you get these values populated in the table as well. So now you can see that after making these design changes, how did the maximum temperature in my heat load change? Did it increase? Did it decrease? Even if, my heat load was higher in this case, by perhaps lowering the grill, I'm getting a benefit in terms of the maximum temperature in my heat load. So really shifting the grill a little bit lower has sort of helped helped reduce my temperature in the domain. So that might be a design decision with which Discovery can help, right? So any questions so far, feel free to leave it in the chat window. By the way, you can also generate a report after you complete all your design studies and all your variations. So if I go ahead and quit this, you could come to this Hamburg menu over here, and you could click on Create Report. What it does is it basically creates an HTML report that gives you all the variations and the important monitors that you were trying to derive out of your simulation results. And let me just go ahead and pull it up. So this is creating the report. And this report can be your one document that tells you how making different parameter changes affected your overall performance or process, right? No matter what you're changing, you could be changing the operating conditions, or you could be changing design parameters. I also had some post-processing scenes inside Discovery that I had created. So these were the scenes that I had created. So these are just similar to post-processing scenes that you could get out of any CFD simulation, different cut planes, different temperatures, velocity, contours. So all of that gets added to the report as well. And then the good thing about this HTML report is all the setup information is available. you could also go ahead and interactively look at your overall geometry. And that can be helpful for anybody who's perhaps not using the discovery simulation tool, but still wants to understand what's happening with the results. So this is just good for team collaboration. Okay. So that's all I had for today's KVA. Let me know if you guys have any questions. If you want to look at the automated workflow of how to create parameters and how to remove a lot of the manual steps that you can subtract from your simulation setup, feel free to reach out to us at support@ketiv.com, and we'd be happy to get back to you with more resources.
Snigdha, thank you so much for your time today. This will be posted on KETIV.com as well as our YouTube channel. And we look forward to having everybody back next Thursday, as well as for some of those manufacturing innovation workshops. Thanks again, Snigdha.
Thank you. Thank you.